Alright, I just showed you how to calculate the moment of inertia of a distribution of point masses, but now we want to look at shapes. And basically the difference between a shape and a point mass is you're not dealing with isolated little masses here. What you're dealing with is, I would say a more symmetrical distribution of the mass here. So if we want to think about various shapes, we would have something like my bicycle, which, you can pretty much ignore the mass of the spokes since they're so light relative to the tire. This is what we would call a thin hoop. Now, there's a lot of different ways to rotate this, but we're going to think about what if this thing were rolling or spinning about the axle like you saw in the bicycle video, pivoting around this point right here, clockwise or counterclockwise. The other thing you can have is you could have something like a disc or a cylinder. So that would be very similar shape, but solid throughout. The hoop has all this empty space in between. So we have disc or cylinder, basically the same thing. After that, you want to think about maybe a ping pong ball, a basketball, something that's hollow in the inside. You have a hollow sphere. A lot of times this may be called thin spherical shell. And then next thing we can think about is something like a bowling ball, lacrosse ball, baseball, something solid. This is a solid sphere. All right, now, again, we're going to be dealing with, think about these things rolling. They're spinning about that axis there, either clockwise or counterclockwise. Basically, we have formulas here that will give you the moment of inertia as a function of the mass of this object and also the dimension. And the dimension we focus on is the radius. So if we want to look at the various formulas for I, and these are on the front of the mathematical packet, the thin hoop is actually the easiest one because it's equal to mr squared, where m is the mass, r is the radius. Your cylinder, it's a little bit different. It's 1/2 mr squared. Hollow sphere, or thin spherical shell, that's going to be 2/3 mr squared. And then your solid sphere is 2/5 mr squared. So what you should notice here is that the objects that have more mass farther away from the pivot point, those are the objects that end up having a larger moment of inertia. Two other shapes we can do are, think about the support beams that I gave you guys. It's a thin rod, so it's pretty linear. We only worry about this dimension here. We do it in terms of its mass and the length, but it depends upon how you try to rotate it. And we really focus on two cases here. We'll either make the pivot point the center or the end. If it happens to be the center, you're going to find that I is equal to 1/12 ml squared. However, if you try and do it at the end, we've seen that that's harder. And that's equal to 1/3 ml squared. All right, so those are the shapes that we're going to be responsible for. There are others out there, but these are the ones we would focus on in this particular class.